talk today. I'm very happy to introduce Timothy Gowers from Collège de France and University of Cambridge. He will talk about what makes solving mathematics problems hard for computers. Thanks a lot, Timothy.
Thank you. Let me know if you can't hear me or anything like that, but I'll just, if I don't hear anything, I'll assume it's okay.
Yeah, we can hear you.
Okay, brilliant. So this title is very sort of wide-ranging and ambitious, and I don't pretend that I'm going to give a complete answer to it. So please lower your expectations before I start. And I should also say that I'm absolutely not a machine learning expert or a formalization expert, actually. So I come to this from two perspectives. One is that of just a normal working mathematician, and the other is that of somebody who's been interested in automatic theorem proving for a long time. So, but attacked using sort of good old-fashioned methods. So the kinds of methods that interest me and have done for a long time are just examining very carefully how I myself and others I know solve problems, and trying to think how a computer could perhaps go about doing so better. So can you now see one slide?
Yes.
And now I've sorted that out. Sorry about that. Okay, so here are some of the reasons that are sometimes given. So a fundamental reason that finding proofs on computers is difficult is, of course, that you're constantly worried about a combinatorial explosion. So you're searching in the space of proofs, and you've got various sort of moves that you can do, or various next lines that you could write down that follow the laws of logic. But there's so many possibilities at each stage that in no time at all you've got an enormous explosion. And yet somehow humans seem to avoid this combinatorial explosion to a very large extent, not at all, but they avoid it to a large extent. And I've put a sort of subcategories of this. So premise selection is a big problem in automatic theorem proving. You very often, if you're trying to prove something, you want to use an existing result, but then there's a vast collection of existing results out there in either in our brains or in the literature. And so how do we choose the one that's going to be helpful to us? And sometimes it's fairly obvious, and sometimes it's quite a lot less obvious. People often talk also about an infinite action space. So again, it's the same sort of idea, but actually the idea that this time that sometimes there are stages or steps in a proof where you've got basically an infinite number of things you can do. So a classic example of this is if you're trying to prove an existential statement. So you want to prove there exists some x with the property px, and you can just build x however you like. Maybe x is a set of real numbers that has such and such a property. Then there's a huge number of subsets of the real numbers, more than uncountably many of them. And even if you just restrict attention to the ones that you can describe, there are still infinitely many subsets of the reals that you can describe. And so when you reach the stage of needing to exhibit your x that will have the properties, then it looks as though you have an infinite set of possibilities. Maybe even if you restrict your attention to the ones that you could write down in a reasonable time, it's still very large and finite. So that's not so much, not quite the same as a combinatorial explosion, because that's a sort of one-step explosion, as opposed to the explosion that happens after you go down a tree, down several steps down a tree. I'm not going to say, I'll say more about some of these things. So another reason that's often given is that this is different for AI being hard in general, is that you need to have models of the world. And this is something that large language models are often accused of being bad at, that they don't sort of have a model of what's going on. And so they'll end up saying silly things about, they'll be bad at problems where you're putting bricks, colored bricks on top of each other, and then sort of knowing which brick is above which other brick and that kind of thing. And that comes into maths, I think, to some extent. I mean, it feels as though some problems we find easy because, for example, we use our intuition about the physical world, or there are plenty of examples of that. Or when we're doing geometry, we use our visual system a lot. And I think those are challenging, but I think they're somehow less fundamental than some of the other questions that I'm talking about. Another problem that's often given is that there's just not enough training data out there. But particularly if you want to come up with formal proofs, then there are some quite big libraries of formal proofs, but they're not somehow big enough, especially with using with lean and various other things like that. But for some purposes, they're just not of the sort of size that one would like to use for training. Again, I'm not going to talk too much about that, although I will talk about training data, but not so much the quantity of training data as the nature of the training data. Another problem is that language models, as we all know, can just say silly things, or can sort of say this works and then provide you with a completely bogus justification. That seems to me, I'm not going to talk about that at all, because that doesn't somehow feel like a fundamental problem. It's believable that it's something that could be sorted out at some stage, that there could be, I mean, it may be technically very difficult. This is where my expertise lets me down. I don't know. But it seems like if it's a fundamental problem, it's a fundamental problem to do with the architecture of language models and not to do with mathematics. So I won't mention that any further. One other problem which is often mentioned is that the question of, where the general question, you're given a mathematical statement and you're asked, is there a proof of that statement, is equivalent to the halting problem. So that we know that there's no algorithm that in general will find proofs for us. Even if we restrict attention to finding proofs when there exist proofs of some bounded length, that's still an NP-complete problem. So not something that we can just expect to be able to do in general. I'll say more about that, but just briefly, why does that not bother me too much? It's because of those words in general. So when we're in practice solving maths problems, we're not solving general instances of the problem. Here is a mathematical statement. Is there a proof of length at most n? But we're actually looking at very, very specific instances of that problem. And there's no reason to suppose that those very specific instances are hard. We're looking at the ones that are, roughly speaking, mathematically natural and interesting. And we're looking for proofs that are sort of comprehensible, explanatory, and so on and so forth. And finding one of those when it exists, there's no general grounds for thinking that that's a hard problem. Okay, so because I'm a mathematician, I think the most useful thing I can do is go through some actual mathematical examples from my perspective, and discuss both the proofs and how to find the proofs and where the sort of difficult spots are for a computer, at least as I see it. And I'm very happy if people disagree with my analysis, because so here's a nice simple problem, or simple problem to state, which is, so by Tetris L shape, I mean one of these things that you see in the diagram. So you have 3 consecutive squares followed by one just out to the side. And you can ask, for which n by n grids can you tile them nicely with these L shapes? And so here's a picture that shows that you can tile a 4 by 4 grid with 4 of them. So first of all, I'm just going to talk you through a full analysis of this I'm just going to give you the analysis. I'm going to sort of lay it out for us, and then we'll go back and think about it a bit harder. So to start with, we can just make the following easy observation. So each square consists of each L shape consists of 4 squares. So the total number of squares we cover has to be even. And so we can't hope to cover an n by n grid unless n is even, because n squared needs to be even. And the second simple observation is that once we can tile a 4 by 4 grid, we can just put together an array of 4 by 4 grids. And therefore, we can tile an n by n grid for every n that's a multiple of 4, just by putting together the solution that we had for 4. So the only case that's left over is what happens if n is even but not a multiple of 4. So for example, if n is, well, a simple example actually, if n is 2 by 2, sorry, if n is 2, so we have a 2 by 2 grid, obviously we can't tile that with L shapes because they're too big. So the first sort of interesting case of this is when n is 6. can we tile a 6x6 grid with Tetris style L shapes? Now, here comes a sort of, the thing I really want you to notice about this is that this step just came totally out of the blue. So I'm just asking you to consider the following way of coloring a 6x6 grid of squares, although actually it works for n by n whenever n is even. So I divide it up into 2x2. On each 2x2 grid, I color red, green, blue, yellow, as I've done here, and I put them all together. Now, why is this an interesting coloring in the context of this problem? It's because if I take an L shape, you'll notice that I can't color I can't cover squares of 4 different colors. I'm always going to have to cover 2 squares of the same color. So for example, if I take a horizontal, say I fit one in the top left-hand corner, so then I'll be covering 2 red squares. Maybe I can just point out, I could cover these 2 red squares in a green and a blue, or I can cover 2 yellows in a green and a blue, or 2 blues and a red and a yellow, and so on. So if you just look, and you can check very quickly that you'll always cover 2 squares of the same color. If that color is red, then the other 2 will be blue and green. If it's yellow, the other 2 will be blue and green. And if it's blue, the other 2 will be red and yellow. And if it's green, the other 2 will be red and yellow. So we've got those 4 possibilities for which colors we cover with an L shape. So now let's just make that, if I order the colors red, yellow, blue, and green, then we get a whole bunch of quadruples that look like this. So this 2, 0, 1, 1 means that one set of colors that we can cover will be 2 reds, no yellows, 1 blue, and 1 green. And this one corresponds to 1 red, 1 yellow, 2 blues, and no greens, and so on. Now we've got, by the end of the tiling, to cover the same number of red squares as yellow squares. So that tells us the number of times we choose 2, 0 at the beginning of our tile has to be the same as the number of times we choose 0, 2. And if we do choose 2, 0 or 0, 2, we'll choose the same number of greens as blues. So I didn't mention, but if we choose 1 and 1 for red and yellow, we don't change the sort of relative difference between the number of reds and the number of yellows. So that's why we have to choose the same number of 2, 0, 1, 1s as 0, 2, 1, 1s. And similarly, the number of 1, 1, 2 noughts is the same as the number of 1, 1, 0, 2s. But that immediately implies that the number of tiles that we use, the number of L shapes that we use, must be even, because we've got to divide them into 2 categories of which we choose, which is sort of have the same number of. I'll go back to the previous diagram in a moment and explain that in a slightly different way. But anyway, the total number of L shapes we choose is even, and therefore the number of squares that we cover has to be a multiple of 8. And for n squared to be a multiple of 8, n has to be a multiple of 4. It's not enough for it to be just a multiple of 2. So that's the end of the proof. We've now shown that you can do it if n is a multiple of 4, and you can't do it if n is either odd or is 2 mod 4. Let me just quickly go back to this picture here. So if you cover this, the number of times you cover 2 reds has to be the same as the number of times you cover 2 blues, because in each case you'll cover, did I say that right? No, sorry, the number of times you cover 2 reds must be the same as the number of times you cover 2 yellows, because in each case you'll cover a green and a blue, and whenever you cover blues or greens, 2 of those will have the same number of reds and yellows. I'm sorry, I didn't quite explain why the, yes, I did. So n squared has to be a multiple of 8, and so n is a multiple of 4. Yeah. Okay, so what I want you to take away from that is not so much the proof itself as the fact that, well, let's just, yeah, is that it contains a number of steps that illustrate this thing about infinite action space, or there's a number of points that are the points where it's not so easy to imagine what a computer would do, particularly if, like a language model, it's doing sort of it's trying to predict the next line of the proof. So early on, in the discussion just now, I just said, well, just notice that we can cover a 4x4 grid with L shapes. And for the purposes of a proof, just exhibiting it like that is absolutely 100% rigorous and satisfactory. But that does leave open the question, how did we actually come up with this way of doing it? In fact, it turns out that if you just do a bit of trial and error, you get to something like this very, very quickly. And in fact, it doesn't have to be that. There are all sorts of ways of doing it. A little bit less, I mean, a bit more sort of rabbit out of hattish is when I said, consider this coloring. So why on earth did we want to consider that coloring? It worked, right? That was easy to check. It did indeed lead to a proof, but it just came out of nowhere. So again, if you're training say a language model to guess what the next line of a proof is, it's very hard to see how it would guess just based on looking at a number of examples of proofs of things. That this particular coloring would do the job. It might see enough of these problems to think, well, maybe this is one of those problems that you can solve by coloring. I think that's conceivable, but then you've that job only half done when you do that, because you've then got actually to find a coloring that's going to work for you, and there are lots of different ways you can color. And there were other moments in the proof that created potential difficulties, like whenever you see something that says observe that, you're just doing some reasoning from what you know to some further stuff, but without really saying where you're going. So this often happens when mathematicians write out proofs. They will write sort of observe this, and then we can do that, and we can calculate this, and we can associate with this, that, and now note that such and such. And then suddenly the proof is over. And again, I feel a lot of sympathy for a language model that's trying to learn how to do maths from those sorts of presentations of proofs. And I'll come back to what the alternative might be. But let's just now say then, just to summarize what the discussion so far, we want what I would call a rabbit out of a hat is anything that where you're not really sure where it came from. So one example is existential statements, where you've got some construction involved, like, there exists a coloring that's going to help us with this proof. And another thing is whenever you just reason from what you know, but drawing conclusions that don't obviously help, that just turn out to help later on. And these are closely related to some of the difficulties I talked about earlier, infinite action space, or the training data. The nature of the training data is sort of unsatisfactory because it's, a lot of proofs are presented in this slightly sort of magic way. And the reason it relates to NP completeness is that with an NP complete problem, a sort of classic NP complete problem is one where you've got to find some needle in a haystack, like a Hamiltonian circuit in a graph. And if someone just magically gives it to you, then you can check very quickly that it works. So I suppose I'm not talking about NP complete so much as just NP. You can check that it works. But there's no obvious way of actually finding it if you're not told it in advance. And a lot of the way proofs are presented has a sort of flavor of an NP problem, or that it's presented as though you required some genius who presents you with the answer with just basically by magic. And but all mathematicians who've actually done research or solved problems at any level, in fact, know perfectly well that's not how things work in practice, and that we spend a lot of time coming up with these solutions. So let me just say a bit more about that. So how would we find a proof like that one? So one thing I've alluded to already is that we have various sort of heuristics that we use. So early on, I used a parity argument, and that's because I've had a lot of experience with those sorts of combinatorial problems, and I know that parity is often useful. And that, again, is something that I can imagine that is not so hard to train a computer to do, just to sort of say, oh, that problem looks like the kind of problem where a parity argument might be useful. And similarly, I know that often for impossibility proofs, I'm looking for something like an invariant or a clever coloring. And so that was not a sort of major difficulty for me as a human. And again, I don't think that's necessarily, you can imagine sort of training a model to recognize whether a problem looks like the kind of problem where looking for an invariant would be a good thing to do. Then another thing that we often do is when we don't know how to solve a problem in general, we have a look at some small case and see if we can solve it in that small case, and then see if we can generalize from the small case. So here, I came up with this example first, but then later I noticed that I could have done it in a slightly simpler way, actually, and just sort of taken two rectangles and put them together. And once I'd noticed that, it was not so hard to generalize from that and get that you could do it whenever n was a multiple of 4. So what else have we got? Well, I've anticipated what I was going to say for 3. So once you've had the small cases, you can learn from them. But another very important thing is trying things and failing, but not just saying, oh, that didn't work, and backtracking and trying something, sort of forgetting all about what you've just done. A very important part of human problem solving, which I'm sort of interested in thinking about, is sort of backtracking as a sort of, you backtrack, but you're sadder and wiser after you've backtracked. So you fail to solve something, and you don't just say, oh, that didn't work, but you say, why didn't that work? And you try to take back some general message from your failure, which you can then use to make the subsequent search more efficient. And that's definitely a big part of human problem solving. And it seems to be quite a difficult thing to get a computer to do, but that's something that people in the group that I have, we're actively thinking about that aspect of human problem solving. Some of you may be familiar with a famous problem where you're supposed to cover, I keep mixing those two words. You're supposed to cover an 8x8 grid with 2 opposite corners removed with dominoes, where a domino is defined to be a 2x1 rectangle. And the sort of famous proof that it can't be done uses a black and white coloring like this, and you just say that each domino covers 1 black square and 1 white square. So once you've seen that, it would be very natural with this L-shaped thing just to say, well, let's just try the normal chessboard coloring and see what that gives. And if you do that, then you see that each L shape covers 2 black squares and 2 white squares, and that's completely unhelpful for that problem, which actually gives you some insight into why the slightly more complicated coloring was used, because this one just doesn't do it. So somehow we want to, once we've done that, what do we learn? We learn that we'd like to find a coloring where it is not the case that each L shape covers the same number of squares of each color. And so that was part of the thought that lay behind the particular coloring. By the way, I actually solved that problem for myself as part of preparing this talk, and that was the proof I came up with. Here's another learning from failure thing. If you actually set about trying to tile a 6x6 grid, you find everything's fine, and you can cover most of it without much trouble. But then suddenly at the end, you seem to get left with, often you get left with a 2x2 square. You can see I could move that blue tile, and I would be a blue L shape, and I could be left with a Tetris sort of S shape thing as well. That's another possibility. But what do I learn from that failure? I learned that I want to have a coloring that will somehow distinguish between the 2x2 square that we don't want to be left with, and an L shape that we'd be happy to be left with. And so the coloring I came up with had the same number of colors in each 2x2 square, but did not have the same number of each color in an L shape. So this sort of example did inspire, for me personally, the coloring that I eventually came up with. Here's another proof. There's a little story here. I talked to an extremely bright Cambridge undergraduate and mentioned that I'd been thinking about this problem. And when I say extremely bright, I mean, well, one of the brightest we've had for a long time, and also somebody with a lot of maths Olympiad experience. And he immediately said, well, I suppose I'd be looking for a coloring. But within about 10 seconds, he had come up with this idea. So which was much quicker, much quicker than it was for me. So it was sort of terrifying to watch him just doing it almost immediately in real time. So why does this coloring work? Well, if you think about what each L shape is either going to cover 3 black squares and a white square, or 3 white squares and a black square. And since there are equal number of black squares and white squares, you'll have to have an equal number of tiles of L shapes that cover mostly blacks as L shapes that cover mostly whites. So therefore you have to have an even number of L shapes. And so again, n squared has to be a multiple of 8, and so n has to be a multiple of 4. If you think about it a bit further, you'll see that that proof is actually sort of similar to mine. It just shows that the proof that I had can be simplified by identifying the colors into 2 classes of 2 colors instead of having all 4 colors. Okay, so here's a proof then, just to speak once more about this NP-ishness problem, that you can just write down an argument like that, which is the argument I've just given. So each L shape covers an even number of squares, and so on and so forth. We defined the coloring, talked about each L shape. Actually, this is an even more concise version, that each L shape covers an odd number of black squares. And so since we've got an even number of black squares in total, we must have an even number of L shapes. So that's actually yet more concise than the version I mentioned before. But that's an easy argument to check, but it's just, there are several steps in it that mean that finding it in the first place is not so easy unless you use the kind of proof finding methods that I outlined that humans use and that I indicated earlier. I didn't indicate them terribly precisely, so I think I'm going to give another example now. Sorry, just one more thing just to drive home the point, because this is the main point I want to make in the talk about this NP-ish problem. So supposing I've got a problem which is to find x, y, and z such that those 3 linear equations are all satisfied. But I gave that to GPT-4 and it had no trouble, and that's not very surprising. But why is it not surprising? Well, it's because there are lots of textbooks that explain to you how to solve simultaneous linear equations, and they don't just explain the method, but they'll give you worked examples. So an obvious theory, I can't claim to be absolutely certain it's true, but an obvious theory for why GPT-4 finds this problem easy is that it's seen a lot of worked examples of solving simultaneous equations. And so then it's obvious what to do next. If it had to invent the entirety of Gaussian elimination from scratch, then I'm sure it would find this extremely hard. But it doesn't have to, and so it can run through the method and solve the problem. Let me just imagine a hypothetical world in which it doesn't have that training data. Well, actually, I'll come to that in just a second. So what happens when we solve an equation is we don't just sort of guess the solution and check that it works. But instead, we take the set of equations and we simplify them until we get to a point where we can solve them easily. So typically, we get them into some sort of triangular form. So one equation involves one variable, one involves one variable and another variable, and one involves, say, all 3 variables. And then we can choose the first variable, and then we can choose the variable from the equation above, and then we can choose the variable from the equation above, and everything is easy. So we first simplify, and then we get the problem to be easy. And that's very, very similar when we've got a much more elaborate existence problem to solve. We typically tend to not to sort of just immediately guess what might work, but instead we mess around with the problem, and we can, when one looks at it more formally, what we're actually doing is some kind of series of simplifications of our hypotheses and our goals and so on, until we massage it into a form where so we just keep the object that we're trying to define as what's the word I'm looking for? Unspecified as possible, and only when we're pretty confident. And sometimes we can't do this. Sometimes we're reduced to having to specify things early on and see whether it works, and if it doesn't work, backtrack. But quite often we can actually not do that. And we can keep things a bit like when we're solving equations. We can keep them unspecified until it becomes easy. But when we then present our solutions, we often just hide all that process and just say, well, this works. We don't explain how we went through the simplification process in order to obtain the thing that works. So there is a quite close analogy between solving more general sorts of maths problems or existence problems and solving equations. So just the hypothetical world that I was going to describe is the world where you imagine a language model doesn't have any kind of worked examples, and the only thing it has is the sort of account that you might get in typical maths papers, where it would just say, to solve this problem, just check that those values work. And if it just had a whole lot of examples like that, then I think it'd be much more inclined just to sort of guess ridiculous answers and claim that they satisfy the equations when in fact they don't, and so on. And unfortunately, that's what I'm saying, is that that's sort of the position it is in when it comes to finding proofs of theorems. It's as though the proofs are presented to it in this sort of style rather than in the style of actually how to solve problems. So let me just, I said I would discuss another example. So this is very explicitly an existence problem. We would like to find an example of 100 consecutive composite numbers. So this is something that you may well have seen this problem, but it doesn't matter if you haven't. In fact, it's better if you haven't. So how do we do this? So I want to describe the, so what I'm not going to do is just sort of write down some natural number n and then try to show that it works, and then show that, sorry, n plus 1, n plus 2, and so on, to show that they all work. Instead, I'm just going to delay choosing n as long as possible. And just, now, what have I written down here? This is the kind of thought that might go on in my head when I would be solving a problem like this. So there's a very important detail here, which is, of course, we want a number n for which those are all composite. But I've added the words, we can prove that. So somehow I want a number n, but I also want to be able to prove that those numbers are all composite. It's not enough if they just happen all to be composite. It might be that n was some number with a huge number of digits, and so I'd have to factorize all of those large digit numbers. That wouldn't be very nice. So what do we say next? Well, all I'm doing now is part of the simplification moves are just basically restating what you had before. So the statement that those numbers are all composite is just the statement that n plus I is composite when naught is less than or equal to I is less than 100. And saying that they're composite is saying that for each of these i's, we can find some factor mi. Of course, mi, I insist, is greater than 1 and not equal to n plus I, a non-trivial factor, mi of n plus I. So that's just repeating what I just said. And now again, I can rearrange. So we would like a number n, and so this, if for each, I'm basically scolemizing here. So for each I want an mi. So that's the same as saying I want a function from 0, 1 up to 99 to up 2, 3, and so on. And I've omitted a condition. I also insist that that I have a non-trivial factor. That's not quite implied by the fact that it's 2, 3, but let's not worry about that. I wanted that as well. I want n to be congruent to minus I mod mi. So n plus I is a multiple of m of I. What have I gained here? Well, it turns out in this case, what I've gained is that this conclusion here, that n is congruent to I mod mi for each I, very closely resembles a result that's in my personal library, namely the Chinese remainder theorem. So the Chinese remainder theorem says that if you've got k numbers and every two of them are co-prime, then given any system of equations of this form, x is congruent to ai mod mi, you can find a solution to it. So you can find some x that's congruent to whatever you like, mod each mi. So if we then apply that, we've reduced the problem very, very considerably, because now we can just take AI to be minus I, as I've said here, and the only thing that we need to ensure is that M1 up to MK are co-prime. So these numbers M0 up to M99 have to be co-prime. So basically, my problem is now reduced to finding 99 numbers that are pairwise co-prime, and that's a much easier problem, which I can use at this stage. I can just do it by greedily doing a few cases and then extending. So I could do it in another way, but here I could just say, what's the first one I could choose? Well, I could choose 2. It's got to be bigger than 1. The next one's got to be co-prime to 2. So the smallest number co-prime to 2 is 3. Smallest number that's co-prime to 2 and 3 is 5. And then I start noticing that I'm just choosing the primes in order. And so I say, oh yes, actually, I could have done that in the first place. I could have spotted that if I just choose the first 100 primes, that's going to do the job for me. And if you just, of course, you then have to go back and say, what does that actually tell you about n? And it, you can work out very easily what n has to be. I won't actually do that. So I've got other things to say. But again, what I want to stress is that if you look in books for the answer to this question, then very often what you see is, let's take n to be 101 factorial plus 1. Why does that work? It's because 101 factorial plus k is divisible by k, as long as k is less than or equal to 101. You can check that very, very easily. And so 101 plus 2, 3, 4, 5 up to 101, they will all be composite. But that's a sort of magic rabbit out of a hat solution. And in fact, just to sort of illustrate my point once more, so if you ask ChatGPT to find 100 consecutive composite numbers, or 500 consecutive composite numbers, it has no trouble doing that, because it's seen that proof in several places, and so it will just make a few small tweaks. If you change the number 100, it has no trouble dealing with that, and so on. But I asked it the question, can you find a prime number p such that, well, no, sorry, I didn't ask, can you find it? It proves that there exists a prime number p. If you ask, can you find one, that's a rather difficult problem. But if you say, prove that there exists a prime number such that the next 100 numbers are all composite. So does that, I'm going to spoil this for you. I'm sorry. I apologize for telling you quite a nice question and then immediately spoiling it. But maybe some of you had time to think how to do it. So actually, this is really quite simple. You just say, we know how to find 100 consecutive composite numbers. So let's just take the number 1, just before they start. We want that to be prime. Well, if it's not prime, it's composite. So let's go to the one before that. Well, if that's not prime, it's composite. So let's go for the one before that. And so the solution would be, just take the largest, take your 100 consecutive composite numbers, take the largest prime number that's smaller than the smallest one, and then the 100 numbers after that will all be composite. But to get that, you need to put in some thought of a kind that's just not out there at all in the textbooks. And it took me, well, actually, I can't remember how I just sort of came up with that problem. But what did GPT-4 do? It kept just sort of trying to say, well, let's pick p and take p factorial plus 1 and things like that, and then tried hopelessly to justify that the number p was prime and there's no reason for it to be prime, and so on. It just tried to sort of copy the proof it had already seen. And a similar thing happened with asking for n consecutive numbers, each of which is divisible by a perfect square. And then the factorial trick doesn't work nearly so well, but GPT tried to make it work. But the Chinese remainder theorem approach works perfectly well for that. You just take a whole bunch of co-prime perfect squares, and then you've got some some congruences to solve simultaneously, which you can do by the Chinese remainder theorem. So just slightly changing the problem causes GPT not to be able to do it as one would expect, because all it's got is this sort of, here's something that works, check that it works type training data, rather than here's how to think about problems sort of training data. So just to summarize what I've been saying, one thing is that there's a strong analogy between the way we find proofs and the way we solve equations. In both cases, we take what we're given. In one case, a list of equations, and in another case, a list of hypotheses and a goal. And we simplify them, and eventually, finding proofs, when I say finding proofs with many features in common with solving equations, I'm particularly talking about, not exclusively, but particularly talking about finding proofs where the main goal is to prove the existence of some slightly complicated object. When I say not exclusively, it's because very often finding complicated objects occurs as sub-goals of the main goal. So for example, in the problem that I showed with tiling with L shapes, finding a coloring that does the job for us was a kind of intermediate goal, and that was an existential problem, even though the main problem showed that you can't tile was a universally quantified problem, that all attempts of tiling fail. But anyway, we have this. So what's the moral I draw from that? It's that in principle, I think one could improve the performance of language models a lot, or transformers in general, a lot, if, and it's a big if, we could create a lot of the right sort of training data. So just as they find it easy to solve equations, if we had a lot of examples where you, which we do have some of, but if we had a lot more examples of just talking the reader step by step through not what the proof is, but how a proof is discovered, what the steps are we have to do to find such and such a proof, then I think statistical methods would perform better. Whether they would be able to perform for truly hard problems, I think is open to question, but I think their performance could improve really quite a lot. But back in the real world, unfortunately, the way we teach proofs, and particularly the way we explain proofs in textbooks, tends to be just by giving the proofs, and so that's turning it back into the sort of it's as though you've got an NP problem that's also NP, but you sort of, when you're presenting it, you pretend it's NP complete. You just give the certificate rather than the algorithm for finding the certificate. So, as I've said here, so one way we might be able to improve things is to improve the training data. Of course, another way is not to use language models at all, but instead to try to use old-fashioned AI-type methods. In other words, just to really think hard about what these proof-finding methods are, up to the point where we can actually program them. Although I think in the end, what I feel most excited about, although I know some people sort of raise their do a bit of an eye roll when people say this, but nevertheless, I'm going to say it. What excites me most is some sort of hybrid approach. So where you have sort of old-fashioned AI methods for doing the kind of what you might call deep reasoning steps of proof finding. But when it comes to the parts, so of course, there's no denying that when humans do these kind of, when they do search for proofs, intuition and various things and heuristics and things do come into play. And I alluded to that earlier on. Just, we have this looks like the sort of problem that you might be able to solve with such and such. So it's highly believable that AI could make a serious contribution, or it could also say, you know, this problem that you're talking about, that reminds me of that problem over there. And then you could say, oh, yes, thank you very much. Yes, I'll go and have a look at that. And then you could look at it and notice that the proof there could potentially, some ideas from the proof could be modified to do what you would like to do for your problem and so on. So I can imagine some kind of best of both worlds approach could be great. But you know, as I say, I'm not an expert. I don't rule out that. I think I do slightly sort of. I feel a little bit skeptical at the idea that increasing the scale or sort of increasing the amount of training data is going to be enough. I just feel that for this, what I call this sort of NP-ish reason, because of the way that we tend to display proofs, I think there will be a serious obstacle unless the nature of the training data changes. And then I think I'm sort of agnostic about whether there's some tipping point at which a language model suddenly doesn't need us anymore because it's got enough sort of proof finding methods and enough other sorts of intuition that it can solve problems of arbitrary complexity, or at least as arbitrary as the problems that a human can solve. But maybe I say agnostic. I think I would maybe sort of, I think if I had to bet, I would bet that scaling up is, and with good training, it's not quite going to be enough for that, but I'm not at all confident of that assertion. I think I'm almost out of time. Yes, I could say more, but I haven't got time to say more. So I'll stop 1 minute early and leave time for questions. So thank you very much for that.